and introducing.
Okay. We've got 35 minutes for Tony
Yeah,
anyway, and he's going to talk about the photon as a problem.
Right, very close to the area of the last one in some ways, but rather different approach. In fact, my whole involvement with ANPA has been because of my interest throughout an engineering life and involved variously with electronic instrumentation and things, over the role of quantum mechanics and the difficulties it creates in engineering because of the inconsistency between the broad approach to modelling and in quantum mechanics. I started at a very early age looking into why it was necessary to have the difference. And having worked on it consistently over many years, I find that it isn't until you get to very high energies where there are some questions, but that doesn't mean that they will not resolve. So anyway, so I'm starting here. I've brought sort of the critical basis of an example of three books there. Unziker's The Higgs Fake. And he's worried about the waste of money in big science. Lee Smolin, he's the trouble with physics. He's worried about waste of time in string theory. You can see the sort of arguments going on there. Karl Popper, in about the 80s, was pointing at schism in physics, philosophical level, which is nearer to what I'm talking about. In fact, I want to go down to an even lower level of the basic considerations of quantum theory. The problems as I see them, if I just go through them as quickly as I can, and then I'll try to expand on some of the points and answer any questions if I can get a little bit of time for that. The modelling the electron from the point of view of electronics is pretty much messy. It compromises contradictory basis, and it's important in engineering because you've got to know, when you're innovating with things, you have to explore areas of new understanding, and you can't really do that if you have to refer back all the time to canonical information. The second point here is the commitment to the particle. Well, the basis of the problem is the commitment to a particle basis is excessive. Photons, bosons, and Fock space, and all that stuff really are in contradistinction to anything of the normal causal basis that is used in engineering. Gauge theories are problematic, and as I see it in the developments I do, the main thing we've got to do is not use electric potential as part of the definitive model. That is only valid in statics. As soon as you go to a dynamic situation, it can't hold a position. Yet we're told all the time we should consider the 4-vector of potentials, that's the magnetic potential, making the so-called magnetic potential 3-vector look like as though it's part of the electric potential. They're nothing to do with one another, and in fact you can get very good modelling of light just using that, what is the anti-curl of the H field and the electric field. Those two together, they form a fundamental basis, and when you use them, you won't need any gauge theories. The advantage of gauge theories, your modelling then evaluates, whereas with gauge theories, you've got to pre-think how you're trying to calculate something. So that's a big problem. So it looks to me as though, basically, the destruction of the photon concept, at least for engineering work, would be a big help, and there's plenty of room to do it. That's what I've been doing my work on my papers are offered on that basis. So, got past the gauge theory and all that. The stuff I've worked on leads to models for electron, and it of course then deals with all the leptons, and the modelling for that is pretty promising. Okay. Dirac's equation creates a lot of the trouble. It starts with a Klein-Gordon idea, and then does 3 modifications on it to twist the existing physics into the picture. Not the least is this stuff invoking Newtonian mechanics to try and force the appearance, the IH thing, so that you get a first order relationship that gives you velocity coming out of the thing. Well, you just don't need it. You can do it that way, but you're carrying Newton on your back all the time. There's the other two, if I can get to them. Anyway, if you just work through the notes, you can find the three things that he puts in. As far as I'm concerned, the Klein-Gordon equation manifests what you might think of as the Broglie wave, which we know exists. It's a wave that travels faster than the speed of light, in reciprocal to the speed of the particle you're considering, and it's got a wavelength in relation to momentum. All of that works okay. You can generalize that beyond the rectilinear motion, and you get the Klein-Gordon model. That's the one that I'm interested in. We've got problems with modeling in the engineering. The engineering main model for electrons to work out molecules and crystals and things is the density functional theory. It has built-in errors, there's no doubt about it. PhDs get written on how to fiddle it right so you get better answers. This is the Kohn-Sham equations, they're called. So obviously, we're not in a good position for doing that work. The exchange correlation hole is what they have. When the electrons get, it's a many-body approach, and when the electrons get too close to one, then you get all the wrong answers. It doesn't integrate up properly. There's so many things. I'd like to go through some of the. Well, let's just finish this bit. There's a problem at the heart of quantum mechanics that people don't consider seriously what is observation. Observation involves physical machinery, be it your eye or your hands or whatever, or instruments made of metal and all that. It requires this physical machinery to amplify a signal. If you don't amplify a signal, there is no way you would see any quantum effects at all. All quantum effects are seen through an amplifier. Now, the thing you've got to add to that is that all amplifiers are thermodynamic. There's no exceptions to this. If an amplifier is thermodynamic, then you do well to take into account how that thermodynamic process relates to what you call the thing you're forming as a reading. For a start, as a thermodynamic amplifier, there is no way that you can amplify that will not produce quantum results. Therefore, seeing quantum results doesn't mean that that's what the process is that would necessarily be generating them. That's a terrible oversight. It is not mentioned anywhere as far as I can see. Has anybody ever seen any mention of that problem? Yeah. The fact that...
But you are saying that to make a distinction is an amplification.
If you want to make a distinction that has some correlative value below the levels of energy that we call the quantum levels of energy, you would not be able to handle the signal. If you try to form a signal, you have to use an amplifier, and the amplifier must quantify. It must give you a quantum result. Therefore, you can't make individual distinctions. You can only make this sort of average distinction.
Yeah. John Bell was well aware of that, right? His lab paper against measurement is worth.
Well, nice point. I'm glad to hear you say that, because I'd also still like to challenge John Bell. And it's the example I'll use in a minute, because it's the most sort of grandiose statement that you've got to have non-locality. Okay, so let's go. That's what I'd like to go at now. So really, my question is, why do people not recognise the essential structure of what is going on, and at least build their answers in connection with that? That's what I'm trying to do, and some of them are successful. In fact, my main problems, they range right out to a cosmological approach. I'm not doing well with modelling the baryons and hadrons yet, but leptons generally in a very nice state, and the amazing way that gravity links into the electron model and produces an onward extension into cosmology is astonishing, and I don't know why people can't be bothered to read it when I present this stuff. It's amazing. So I'll leave some time for questions, but let me just try to point at the sort of things that are wrong with the model of the electron. We've got one that's a glaring one, comes out all the time. Intrinsic spin. People go around saying an electron has a magnetic moment due to intrinsic spin. Well, it doesn't. It's not even. It's just not there. There's only 1% of people who will ever say anything about it. It has a paramagnetic moment. And a paramagnetic moment is just different modelling. We need to get these things right in order that we can start putting things together properly. The only time you get a magnetic moment all the time off the spin is when the orbital spin is coupled to the intrinsic spin, and that causes the paramagnetic moment to generate a fixed value then. But if there isn't any orbital spin, you don't get any intrinsic spin effect. So we're just looking at things the wrong way to try and do those things. There's another one here. One that is a big one for me. The old ultraviolet catastrophe problem, that if you had a thing like an electron orbiting, all its energy would be thrown up into the high frequencies and disappear, and the electron would fail and stop to exist. Well, it's not just true with orbiting systems, it's true with vibratory systems as well. So whichever model we use, we're going to get that picture. So we want a system of either orbital or vibratory. I'm more interested in the vibratory ones that will not show that effect. Physics hasn't done that, but there is at least one model, the one I use. If you recognize the first of all, you've got to recognize that the charge and current are generated by some sort of field. I'm interested in field models. I don't think you can do this with orbital models, but with a field model you can. You can show that there's a commutator type of the psi star psi type of Schrödinger charge density, and psi star d by dt for Dirac. Well, if you modify that again and introduce a Hilbert transform in that commutator, then the electron suddenly comes alive. It does all its things. It doesn't upconvert energy, and it doesn't either suffer from radiation from the electron itself or interaction of electrons. They both go dead, except when you move away from the quantum state. It does what the electron does. Okay, this model does. So nobody says anything about this model. I only seem to have seen it. Curious. And if you use this model, then you may start to build the atom of a piece. You can put the electrons in, and they all form eigenfunctions. And to my astonishment, I didn't expect this. I just built that because I could see it coming. But you find that because you've got intensity of the field of the electron, this is a scalar complex field. Don't call that psi, it's not quite the same as the quantum mechanics. Because you've got intensity there, it means that we're looking at a quadratic in the linear psi variable. That is multiplied back into the matrix. So this gives us a fully self-coupled electron, and that's a cubic closure. You've got a quadratic multiplying in as coefficients, and that loop is a cubic. And immediately, if you know anything about solitons, you know that a cubic is very important as the basis of making a stable, regulated entity in a vibratory form. Nobody does it for some reason, but it works. In fact, you can then start looking at what the cubic is like in this rather wobbly soliton thing.
Can I ask a very quick question, Tony?
Yes.
So in your model, which I'm afraid I'm not familiar with, is there some kind of underlying nonlinear field theory picture
No.
of the electron?
None at all.
Or then
Astonishing
where the solitons coming in, really?
Right. Where's the cubic come in?
Yeah.
Well,
You said it's reminiscent of
you're
soliton
making
solutions, so
jumps.
that's...
But that's been a big question for me. The fact of the matter is that the system sits, you've forced me into a much deeper model. There's an under model, which is the quantum foam, except it's a wave quantum foam, okay? Its equation is D'Alembertian. The D'Alembertian is order 3 in space. The closures of that have got 3 orders, that matters, but that last point is not relevant to this. Sorry. When you put together this linear process, then the correlations created start to show nonlinear effects. You get nonlinearity in the correlations.
Okay, right.
So if you want to use this model, you've got to realise that our whole existence is merely a correlative existence over another foam C. Okay.
So it's a non-linear, but the non-linearity
It's a
is a kind of effective notion coming out at a
this is
high
the thing that
level.
worried me a lot, because I think, how can you get nonlinearity emerging from a linear system? You can't in the direct sense,
No.
but in the correlations you can.
Okay.
This is news to me, and we use the term linear in the 2 senses.
Yeah.
Linear system, what you call distributive type of coefficients, and the linear coefficients of the equation. Well, you can have linear coefficients of the equation and get non-linear closure of the correlation dynamics.
Yeah, I'm getting the picture. That's very,
And
very, very
we
helpful.
are correlations. We are not the raw material, as you might say.
Understood.
That's the way that works. Well, that's to say there is one model that does it. I'm not going to say it's right, but when there's one, it matters.
Yeah.
So I think that's probably about as much as there's more things about the electron. I mean, the electron's beginning to be filled in when you've got these things. You've got a real thing that works, not bits missing that have been dictated as being chopped off. Okay. So I suppose what I'd like to do is as much else. One thing I would like to do is take up the egregious claim that because the photonic coupling between 2 detectors with a converter, a parametric down converter, shows synchronism at the ends, there must be superluminal communication. That isn't true. First of all, you put it together in ordinary electronics with a down converter made of a modulated diode, and you'll see that, I'll just draw it on here. What you've got is a detector. Let's say that's a detector. And you've got a light path between it. This is usually both polarizations. It's a order 2 vector. And then you put a device in the middle here, which is called a parametric down converter. It's a degenerate parametric down converter. This is all the communication stuff. And you allow light to travel both ways in these. And in here you inject, it's a laser that's used here, in light obviously. There's various reasons for doing these various things, but this is a very precisely set up system. And the precisions of it, like the narrow band of the laser, and in particular the cable having a very low dispersion, that means the speeds of all the waves in it have got to be the same. These are things, and the crystal that works in here, are all excruciatingly accurately aligned. And they're excruciatingly accurately aligned so that the wave phases will stay in line. And then they consider that there's photons operating in it, which completely throw away the idea of this excruciating. The laboratory work to get the phases of the waves is unbelievable in these things. And to complete this, we'll just have a comparison down here. This is the comparison system. So the idea of a photon coming down here and occasionally, about 1 in 10 to the 12, creating a pair of photons going out here is just odd. For a start, we can say there's a crystal in the front of each of these, a photodetecting crystal, and the efficiencies of those crystals to convert light into these electron pulses is in the region of 5 to 8%. There will be a little bit of light converted otherwise and lost, but in fact most of the light goes back straight down this channel. 90% of the light that goes in there comes back out again. This system's alive with light going both ways. Now, when light comes through a parametric down converter, then the spectrum of the light is inverted. So the light that's transmitted this way, these are two separate crystals. The crystal motion, they've got billions of atoms in there, and therefore billions of modes in the particular pair of levels that are forming the optical process. And they result of their repulsion of each other, the way that the eigenfunctions form. The crystal has about an octave of frequencies that are visible. So when a pattern of light is coming through here, its spectrum is inverted here and arrives at this end. So now you've got B, which is by means of a prediction is conveyed over to here, so that it's in the same state as it was when it was emitted over there. A is doing the same thing that way. So now we've got a co-timed A star B here, and B star A over here. Well, it happens that A star B and B star A give the same product. And it's those products that cause the electrons to jump out. That has nothing to do with superluminal communication. That's the ordinary way that a down converter works. It's entirely expressible in wave processes, and all this gummery you have to do to keep it accurate is because you're keeping those waves in time. A little bit of dispersion wouldn't worry the odd photon, I would have thought, but it does worry the waves. It knocks them out of phase with one another, excruciatingly close it has to be. This result is proposed on the basis that it probably happens between stars. That's madness. You can't do that sort of thing. So, we don't need the photon in this position. We've got to start modelling with what actually works. So, that's the picture. Any questions? Sorry, you finished.
May I? Basically, your argument seems to me the opposite of Peter's argument the other day, when Peter was arguing there is no classical mechanics, and you are arguing about not being so confident about quantum mechanics.
No, the quantum mechanics is there, but you have to arrive at it through a process of some wave-based thing. The photon is the problem.
Have you looked at all at Sachs's nonlinear spinor field theory? He has exactly this program.
I'd like to get that.
He derives the photon as the very weak coupling limit of an underlying nonlinear spinor field theory. The only thing is that his is fundamentally nonlinear to begin with, so it's unlike yours. He's not thinking in terms of some more fundamental level of quantum foam, waveforms. So the nonlinear. Oh yes, he's worked out a whole series of papers from the 60s to the late 70s, which were published mainly in Novo Shemenko and elsewhere. So I'll give you the references to that. Mendel Sachs. Yeah.
No, but my point was that you should make an argument of the same kind for ordinary perception and ordinary observation, thinking about the physiological, neurological...
that's what my life I've been making that argument in my own mind, joining those together.
Well, when you mentioned about thermodynamic effects had not been taken into account, I mean, the fact that the fact everybody quotes about the dark adapted eye being capable of detecting bursts of whatever it is, 3 or 4 photons, I mean, that completely fails to take account of the fact, as you say, the eye is, of course, a thermodynamical system. It's
rather easy in those areas to see the problem.
Yes, you see the problem straight away there.
Can I, the point about observation and amplification, so you're saying that observation must entail amplification of the signal.
Well, if it doesn't, you won't be able to put it into an...
Okay. How would you distinguish between amplification of the signal and attenuation of the context?
Well, the context has got a thermal level, and you could change it and reevaluate. But the point is, you've got to get the signal well above that because you have to record it. You have to be able to repeat the thing.
Yeah, but it could be a constraint thing, couldn't it? It doesn't have to be amplifying the thing that you're observing. It could be actually eliminating the things that you're not interested in.
If you have a complete amplification and recording system near absolute zero in temperature, yes, it would work out at that level, but it's the same problem. It's an entropic problem, not a temperature problem. You have to have that name.
I reckon something has to be going on, certainly. Some work has to be done.
And it's an ordinary thermodynamic, it's a heat engine.
Yeah.
Okay.
What do you say about the current experiment G-2 for measuring the magnetic moment of the muon to an accuracy unprecedented in the history of physics? 1 in 10 to the 12, 13 or something.
Well, there's no problem with doing the measurement as long as you've got the negative entropy available. As long as you can amplify, we've got this organised, it's a very accurate result. It's the most accurate in its class, that's all that is. But of course, I'm not saying we can't do measurements, I'm saying you can't do them. There is an ultimate level where you lose sight if you're not using an amplifier. That's the point.
Any more questions or
I just want to clarify, so what you just discussed, experiments that can be found here, right? In this.
Oh yes, there are some references I've given in those notes, yes. There's three sets of notes here, and there's a website there. You can infer the website from it, you can dig around in there if you want, and you'll find stuff. Okay.
So, any further questions or comments? We thank Tony again. And come back at 1:15.